Good morning, guys. In previous lecture we have studied actually about CST element. We have discussed the things related to your CST element. CST element is what? Your constant strain triangular element. Okay, so why it is called as constant strain triangular element? Because the strain remains constant within the element. Okay, so that's why we call it as a constant strain triangular element. Okay, so for CST element we have discussed or we have taken all the things related to your CST element. Means what is the displacement function, what type of displacement function should be used for this CST element. Means as we know that CST element is nothing but constant strain triangular element, so we need to add constant linear terms. Okay, so we need to add linear terms into the elements, into this displacement function. So for this linear displacement function we have added our linear terms here. A2x and A3y, these are the linear terms we have added for the convergence requirement. Okay, so we have studied the CST element, then we have studied the displacement function, selection of displacement function, then we have taken the shape functions as well as the coordinate system. We have studied the coordinate system, then we have studied also the n1, n2 and n3 values. Okay, so as we know that for numerical purpose, what is the value of n1, n2 and n3 for this CST element? So n1 is equal to zeta, n2 is equal to eta, and n3 is equal to 1 minus zeta minus eta. Okay, so by using this n1, n2 and n3 you can find out the your x and y coordinates. Okay, so x and y coordinates are x is equal to n1 x1 and 2 x2 and 3 x3. Similarly you can find out y. So okay, so in this way we have studied CST element. Okay, now we will study, or we can start our next topic, means linear strain rectangular element. Okay, this linear strain rectangular element, it is nothing but a 4-noded rectangular element. Okay, then why we can call it as a linear strain rectangular element? Because the strain is constant within the element, so that's why we can call it as a linear strain rectangular element. Okay, so this linear LSR element, it is used in the analysis of plane 2-dimensional problem. Okay, and this is the figure of this 4-noded rectangular or linear strain rectangular element. Okay, so similar to CST, there are four nodes, means 4 coordinates should be there. So for first node x1 y1, for second node x2 y2, third node x3 y3, fourth node x4 y4. Okay, so here we can write our displacement function. Means as we know that the displacements, u generalized displacements is u and v. U is in x direction, v is in y direction. So we need to write down the displacement function. So displacement function can be written as we know that this is linear strain rectangular element, so we need to take into account the constant term as well as linear term. So this shape function can be written as a1 plus a2x plus a3y plus a4xy. So this a2x and a3y, these two terms are added to have a constant strain requirement. Okay, so similarly you can write v as a5 plus a6x plus a7y plus a8xy. So in this way you can write generalized displacement functions as u and v. Now by using these generalized displacement functions u and v, you can write now nodal displacements. So as we know that as there are 4 nodes, so 4 nodes, at each node there are 2 displacements, u1, capital U1, capital V1 for node 1, then for node 2 capital U3. Here Q3 and Q4 we have taken, but capital U3, U2 and V2. For third node U3 and V3, and for fourth node U4 and V4. So similarly we can write this nodal displacements for LSR as U1 is equal to, so by using this U and V values we can write nodal displacements as U1 is equal to A1 plus A2x plus A3y plus A4 x1 y1. So by using these U values you can write, okay, so by using this U value you can write here nodal displacement is U1. Similarly by using this small v value you can write V1 as, it can be written as A5 plus A6 x1 plus A7 y1 plus A8 x1 y1, x1 y1 because for first node the coordinates are x1 and y1. So similarly for second node you can write in terms of x2 y2, for third node you can write it in x3 y3, and for fourth node you can write it in x4 y4. Okay, so similarly you can write, so in this way you can write the nodal displacements u1 v1, u2 v2, u3 v3 and u4 v4. Now next is what? Now we need to see the shape functions. We need to find out the shape functions for the LSR element also, because as we have determined the shape functions for the CST element, so similar way we need to find out the shape functions for the LSR element. Okay, so for LSR element the natural coordinate system is given as, so look at this figure, this is the natural coordinate system for the LSR element. So in CST element, actually, as we know that for CST element the natural coordinates eta and zeta we have written as, for first node, look, for this natural coordinates, okay, this is for your CST element natural coordinates zeta and eta. We have written zeta and eta as, zeta is equal, for node 1 zeta is equal to 1, eta is equal to 0, for node 2 zeta is equal to 0, eta is equal to 1, and for node 3 both values are 0. So we need to write down now the natural coordinates for LSR element. Now for LSR element the natural coordinates can be written as, this is the natural coordinates. So for LSR node we can write the natural coordinates zeta and eta as, for first node, look, this is the first node, for first node, as we know that this is your fourth quadrant. Okay, so as we know that the zeta, these values lies between -1 to +1, zeta -1 to +1 it will lies between, similarly eta also lies between -1 to +1. So we can write zeta and eta by using this system, as we know that for fourth quadrant. So okay, how to remember this eta and zeta? Okay, so as we know that this first node it is in fourth quadrant, so for fourth quadrant both values, if we are considering x and y coordinate, for fourth quadrant we know that both values x and y it should be negative. So similar way we can remember that the first node is lying in between, first node it is lying in quadrant fourth. So for fourth quadrant both values are negative, so we can remember that zeta and eta is equal to negative, means -1. So look, so for first node zeta is equal to -1, eta is equal to -1. Now your second node it lies in, sorry, I actually did a mistake. Actually for your first node it is in third quadrant. For third quadrant both values are negative. Okay, and this second node it is lying in fourth quadrant actually. So for fourth quadrant your x is positive, y is negative. So similarly here zeta is positive and eta must be negative. So this is +1 -1. Okay, so this is zeta is equal to +1, eta is equal to -1. Similarly your node 3, third node, it is lying in first quadrant. For first quadrant we know that both values are positive. So your for third node, so node 3 +1, and similarly your fourth node it is lying in second quadrant. For second quadrant x is negative, y is positive, means zeta is negative, eta is positive. So for your fourth node zeta is negative, eta is positive. Okay, so these are the shape functions. So shape functions, so how to remember shape functions? At node 1 n1 must be 0, other three are at node 1 n1 must be 1 and other three values are 0. At node 2 n2 must be 1, other values are 0. At node 3 n3 is equal to 1, other 3s are 0, and at node 4 n4 is equal to 1 and other 3 are 0. Okay, so in this way you can remember the n1, n2, n3, n4. Now we need to write down the expression for the shape function here. Okay, so as we know that the expression for the displacement function is given as equal to a1 plus a2x plus a3y plus a4xy. Similarly we can write the shape function expression with the help of this displacement function. So it means what? Generalized n shape function n will become, so okay, the shape function generalized shape function n will become this a0 plus a1 zeta plus a2 eta plus a3 zeta eta, or we can say instead of a0 we can say here a1 plus, okay, instead of x and y we need to put here zeta and eta. So a1 n is equal to a1 plus a2 zeta plus a3 eta plus a4 eta zeta. So we can write this shape function in this way. So n is equal to a0 plus a1 zeta plus a2 eta plus a3 zeta eta. Now for node 1 we can write n1. So n1 it will become, for node 1 we can write n1. So n1 will become a0 plus a1 zeta plus a2 eta plus a3 zeta eta. Now for node 1 we need to put the values of zeta and eta as well as the value of n1. Okay, so by putting these values we will get first equation. For node 2, as we know that for node 2 n2 is equal to 0 for first condition, so we need to write down these three. Okay, in this way if we put for node 2, node 3, node 4, we can get these 4 equations, and by solving these 4 equations we will get the values of a0, a1, a2 and a3. Okay, so therefore by putting the a0, a1, a2, a3, a3, we will get the shape functions n1, n2, n3 and n4. So now n1, look at this, n1, what is the formula for n1 shape function? N1 is equal to 1 by 4 in bracket 1 minus zeta into 1 minus eta. Okay, 1 by 4, this is a quotient, means this is the constant 1 by 4 into the whole term 1 minus zeta into 1 minus eta. So how to remember the shape functions n1, n2, n3, n4 for the LSR element? So as we know that from a quadrant system, your first node it is lying in third quadrant. For third quadrant both values are negative. So similarly n1, 1 by 4 is constant into both values are negative for first node because it is lying in third quadrant. So it can be written as 1 minus zeta, 1 minus zeta. Similarly your second node lies in between fourth quadrant. For fourth quadrant your x is negative. X is negative means zeta is negative. So sorry, x is positive. X is positive means zeta is positive. So 1 plus zeta, 1 minus zeta. Then your third node, it lies in between first quadrant. For first quadrant both values are positive, means 1 plus zeta, 1 plus zeta. And for fourth node, n4 is equal to, for fourth node it lies in second quadrant. Second quadrant the value of zeta is negative, so 1 minus zeta and 1 plus zeta. So in this way you can remember the n1, n2, n3, n4 values. Okay, so by using this n1, n2, n3, n4, now we can write the coordinates, generalized coordinates for any point P within the element as x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Similarly y is equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. Okay, so such type of examples will be asked in your exam, like they have given the zeta and eta values and x1 y1 x2 y2 x3 y3 and x4 y4 values. Then first we need to find out the shape functions n1, n2, n3, n4 by using this eta and zeta values. Okay, so by using this eta and zeta values you will get n1, n2, n3, n4. Then by putting n1, n2, n3, n4 values into these two equations x and y, you will get the coordinates for P. Okay, means x and y. So in this way you can solve the coordinates for this LSR element. Okay, so just similar to the CST element, we need to determine first the shape functions, then we will get our coordinate values x and y. Okay, so such type of problems will be asked in your exam for CST element as well as for LSR elements. Okay, so in this way we have covered our LSR elements and we have covered our third chapter also, or third unit also, two-dimensional elements. So two-dimensional elements, it is not in two-dimensional elements I will just revise this syllabus we have covered. So first we have covered the basics of the two-dimensional elements. What is the basic difference between 1D, 2D and 3D. Then we have covered the basic two-dimensional elements. Then we covered the conditions, the plane stress condition, plane strain condition. Then we covered actually next the Pascal's triangles, means polynomial shape functions, how to remember the two-dimensional polynomial shape functions. So to remember the two-dimensional polynomial shape functions, we have used our Pascal's triangle. Okay, so Pascal's triangle, it is the convenient way to remember the two-dimensional polynomial shape function. Then what we have discussed, the convergence requirement. There are 4 conditions we need to satisfy while selecting the displacement function. Then we have covered the two-dimensional elements, means basics of your CST element. Then in this lecture we have covered the LSR element. Okay, so in this way we have covered your third unit, means two-dimensional elements. Okay, so this is about your third unit. Now from next lecture we will start our fourth unit, that is isoparametric element. Okay, so here I am concluding this lecture here only. So thank you.